You've seen the videos. A cruise ship tilts hard in open water. Furniture slides across the deck. Passengers grab anything bolted down. And for a few seconds it looks like the whole thing might just keep going. These ships are floating skyscrapers. 20 stories of glass and steel carrying 5,000 people through waves that rip containers off cargo vessels like loose bricks. The physics say a structure this top-heavy should roll over. It doesn't, and that's not luck. Between the ocean trying to tip the ship and your champagne glass staying perfectly still, there's a war happening beneath the waterline. Every ship afloat is caught in a balancing act between two invisible forces. The first is gravity, pulling the entire weight of the vessel downward through a single point called the center of gravity. The second is buoyancy, the ocean pushing back upward through a different point called the center of buoyancy. In calm water, those 2 points line up vertically, and the ship sits perfectly stable, as steady as a building on solid ground. Then the ocean moves. As a wave passes beneath the hull, the water level rises on one side of the ship and drops on the other. That shift moves the center of buoyancy sideways, and suddenly those two forces are no longer aligned. The gap between them creates a tipping force, and the ship leans. The bigger the wave, the further the buoyancy shifts, and the harder the lean. A small wave barely registers. A large swell with a long wavelength can push the ship into a slow, heavy roll that passengers feel deep in their stomachs. But here's the thing most people get wrong about that rolling. It's not actually dangerous. A well-designed ship leans into a wave and then recovers, rocking gently back to center as the wave passes through. The hull shape, the weight distribution, the underwater geometry, all of it is engineered to make the ship want to return upright. Gentle rolling is the system working exactly as intended. The ship was built for this. The danger isn't a ship that rolls. The danger is a ship that rolls and doesn't stop. There's one specific condition where the ocean stops nudging a vessel and starts feeding it energy, amplifying every roll instead of letting it settle. It has nothing to do with wave size. It has everything to do with timing. Every object that can swing has a natural frequency. A playground swing, a pendulum, a wine glass tapped on the rim. Ships are no different. Push a cruise ship sideways and release it, and it will rock back and forth at a specific rhythm determined by its hull shape, its weight, and how that weight is distributed. That rhythm is the ship's natural roll period, and most of the time, ocean waves have nothing to do with it. But occasionally, the ocean gets lucky. The interval between wave crests matches the ship's natural roll frequency exactly, and something dangerous begins. Each wave arrives at precisely the moment the ship is already leaning in that direction, adding energy instead of disrupting the motion. The effect is identical to pushing a child on a swing. Time your push with the swing's rhythm, and a small force builds enormous motion. Mistiming it kills the momentum. The ocean doesn't need to push hard. It just needs to push at the right moment, over and over. This is synchronous rolling, and it can escalate with terrifying speed. A ship rocking 5 degrees suddenly hits 10, then 15, then 20. The rolls don't level off because every wave feeds the next one instead of fighting it. The crew feels it immediately, a rhythm that isn't settling, a lean that gets worse instead of better. If nothing interrupts the pattern, the angles keep climbing until the ship reaches a point where its own stability can no longer pull it back upright. The ocean doesn't need a monster storm to threaten a vessel this way. It needs the right wavelength at the right angle for the right duration. That's the engineering nightmare every stabilizer system on a modern cruise ship exists to prevent. A force that reverses direction every few seconds, never stays constant, and punishes any system too slow to keep up. The simplest weapon against rolling has been around for over a century, and it's about as low-tech as marine engineering gets. Bilge keels are long, flat strips of steel welded to the curved underside of the hull, running along the bilges where the bottom of the ship meets the sides. They look like fins that never move, because they don't. There are no motors, no sensors, no hydraulics. Just metal, bolted to metal. Their job is pure resistance. When a ship rolls, the bilge keels drag through the water, generating turbulence and opposing the motion. The physics is straightforward. You can't move a flat plate sideways through water without the water pushing back. That pushback slows the roll, shortens the lean, and gives the ship's natural stability a better chance to pull the vessel upright before the next wave arrives. They're cheap to build, easy to install, and nearly impossible to break. No moving parts means nothing to maintain, nothing to fail, and nothing that needs power. That combination makes bilge keels one of the most common features on large vessels worldwide. Cargo ships, tankers, naval frigates, nearly every big hull riding the ocean right now has a pair of bilge keels quietly doing their job beneath the waterline. But passive resistance has a hard ceiling. Bilge keels can only fight a roll that's already happening. They can't anticipate the next wave, they can't adjust to changing conditions, and they can't generate force on their own. They dampen motion. They don't prevent it. For a cargo ship carrying steel at 12 knots through open ocean, that's usually enough. For a cruise ship where 3,000 passengers expect to walk a straight line, eat dinner on white tablecloths, and set a champagne flute on a table without thinking twice, dampening isn't even close to sufficient. The ocean needs a smarter opponent. If you can't outmuscle the ocean with steel plates, maybe you can fight water with water. Anti-roll tanks take the same force that's trying to tip the ship and turn it into a weapon against itself. The concept is deceptively simple. Install large tanks on both sides of the vessel at the widest points of the hull, connect them with crossover pipes, and fill them with fluid. When the ship leans to one side, gravity pulls the fluid toward the low side. In a basic passive system, the engineering trick lives entirely in the pipe design. Control the diameter, the length, the restrictions inside those crossover pipes, and you control how fast the fluid moves. Get the timing right, and the maximum weight of fluid arrives on the low side at exactly the moment the wave crest is generating the strongest tipping force, pushing back against the lean instead of adding to it. Then the wave passes, the ship begins to roll the other direction, and the fluid needs to shift back across to meet the next crest, coming from the opposite side. The entire system is a constant race against the rhythm of the ocean, shifting thousands of liters of water back and forth in sync with waves that never arrive at the same interval twice. Passive tanks rely on gravity and geometry alone, which limits their precision. Add pumps and gyroscopic sensors, and you get a fully active system that reads the ocean in real time and forces water wherever the math says it needs to be. These active tanks work well. They can counter rolling forces as they happen, adjusting to changing sea conditions without any human input. But water is heavy, and pumping it across the width of a ship takes time. Seconds matter when a wave is already tipping the hull, and the ocean doesn't wait for plumbing. The roll is half finished before the tank catches up. Beneath the waterline of almost every modern cruise ship, there's a pair of wings most passengers will never see. Fin stabilizers are hydraulically operated blades that extend outward from the hull into the water, and they solve the one problem every other stabilizer system struggles with: speed. The mechanics are borrowed directly from aviation. Each fin is shaped like a short aircraft wing, and it works on the same principle. Water flowing across the fin generates lift, and the direction of that lift depends entirely on the angle of attack. Tilt the leading edge upward, and the water pushes the fin down with enormous force. Tilt it the other direction, and the force reverses instantly. No pumping, No waiting for fluid to shift across a ship. Just a hydraulic rotation that takes a fraction of a second. The brain behind the system is a gyroscopic sensor package that reads the ship's motion in real time, measuring roll angle, roll speed, and wave timing simultaneously. That data feeds into a control system that adjusts the fins continuously, rotating them to counter whatever force the ocean is applying at that exact moment. A wave pushes the ship left. The fins generate force to the right. The wave passes and pushes the other direction. The fins reverse before the roll even begins to build. The response is so fast that passengers feel almost nothing. The ocean is still throwing the same waves, generating the same forces, but the fins are canceling them below deck before the motion reaches the surface. What makes fin stabilizers dominant on cruise ships isn't just their speed, it's their versatility. They counter wave-induced roll, but they also fight wind pressure on the ship's massive superstructure, compensate for the vessel heeling into hard turns, and even push back against the subtle weight shift of 3,000 passengers migrating to one side of the ship to watch a sunset or crowd a portside railing during arrival. This is the system that keeps the champagne glass still, not hull shape, not ballast, not the ship's raw size. Underwater wings reading the ocean hundreds of times per second and fighting every force that tries to tip the vessel before you ever feel it happening. But every system has a weakness, and fins have one that changes everything under the wrong conditions. Fin stabilizers have one vulnerability that most passengers never think about, and it's built into the very physics that make them work. Fins generate force from water flowing across them. No flow, no lift. Below roughly 6 knots, the water passing over those hydraulic wings simply isn't moving fast enough to produce a meaningful righting force. The fins are still there, still extending from the hull, still rotating on command, but they're pushing against water that isn't pushing back. A cruise ship dead in the water during a storm has effectively lost its most powerful defense against rolling. The gyroscopic sensors are still reading the waves, the control system is still issuing commands, and the fins are still moving. None of it matters. The ship is back to relying on hull geometry, bilge keels, and whatever passive stability the designers built into the structure decades before the vessel ever met this particular storm. This is why speed and stabilization are quietly inseparable on a cruise ship. The vessel's best defense against capsizing is, counterintuitively, to keep moving. Forward motion is what gives the fins their power. The moment the ship loses headway, the system that cancels 90% of the roll goes silent. It also explains why slower cargo ships rarely bother with fin stabilizers at all. Their typical cruising speeds sit too close to the threshold where fins become useless, making the investment hard to justify. Those ships rely on bilge keels, tank systems, and sheer mass instead. Most cruise ships never come close to this vulnerability. Their normal operating speeds sit comfortably above the minimum, and modern routing keeps them away from the worst conditions. But the engineering truth remains: stop the ship, and the fins stop fighting. Next time you see a champagne glass sitting perfectly still on a cruise ship table while 15-meter waves roll beneath the hull, that's not the ship being too heavy to move. It's hydraulic fins beneath the waterline reading the ocean hundreds of times per second, rotating underwater wings you'll never see, fighting a war against physics in real time so you don't feel a thing. But keeping a ship upright isn't even the strangest engineering problem cruise lines have solved. How these vessels float at all while weighing over 200,000 tons is a story that breaks most people's intuition. That one's next.